And we are back. Streaming preview. The streaming preview is here, and I should hear myself. Let me check with my headset. Yep. Okay. Audio works, and yeah, back. I had enough time to drink a bit, and that's it actually. And fix the HDMI grabbing. It's just that the USB somehow got broken, and the HDMI grabber weren't recognized anymore by OBS, and OBS didn't want to check again. So we are at the same setup. We left part 1, but we will update the notes because the notes are quite out of date. So see previous part at DMX control DC motor. DMX DC motor. DMX explained in previous parts. What we see is we saw that we have solid state relay with 0 crossing only allows to switch half cycles to switch on off 50 Hertz means half cycles. The SCR, I think this is how it called the machine, uses a triac allowing any duty cycle within half cycles, within half cycles. That's what we've seen about the SCR. The problem with the SCR is mains referenced as main uses mains earth as 0 volts for the digital part. Digital parts, so, and the SCR does not provide enough current for the ESP8266. So we changed from using the SCR to we will use AC dimmer module. We will have our own supply, have our own power supply. And I've checked actually with the Robodin. This is the Robodin. I don't know what the reference is, but I've checked online and in the data sheet. Well, how is it called? But that's not the right one. Somehow I went to the Robodin official store on AliExpress. I don't know how official it is, but PSM stands for PWM, pulse width modulation, because this is how you switch on the thing. So yeah, I'm not sure how well they did it. ACDMA module, genau, exactly. We will have our own power supply, and this is the stage we are at. We have the power supply. We didn't test the Robodin module, the ACDMA module. This is what we will do now. So camera is here. I have to switch. So we will switch to the oscilloscope. Yep, this is, why do I have 3 ones here? This one removed. This is the oscilloscope. This should be also refreshed every 2 seconds. Yes, it is refreshed. And the HDMI grabber still works. Can I see my hands? Yes, this works. I flipped. I just realized now that this camera wasn't flipped because it is upside down, but it wasn't flipped the other way. So now you should be better. Let's get back to the oscilloscope. With the oscilloscope, we want to see actually how this module here works. Let's put the camera better here. How this module works. More precisely, well, the PVM is probably, because it uses an optocoupler with a diode, it's probably you have to put it high to send a pulse and enable the triac. What I'm interested is the zero crossing reference. How does it do? Does it just pulse every time you cross a zero? Is it high whenever it is AC on and low whenever? Well, how is the output of the signal? What does it correspond to? So we will connect the multimeter to the output of the PS of the module. So let's connect. My arm isn't long enough. Let's connect ground, and we'll use a green cable. Did we use green? The third pin, zero crossing. Yes, that's zero crossing. Let's switch on the power. Power is switched on. We see it with the LED of the board. And online on the digital, we have to switch the voltage when not here. 5 volts, 1 volt. Okay. Up. Tuck. Here. 100 Hertz. Okay. So how the zero crossing works is what you see from the multimeter. I call everything which measures something a multimeter because it measures, at least it meters something. But I meant the oscilloscope. So what we see here is 100 Hertz, meaning that at zero crossing there will be a high pulse. This is how we will see it. So it's not on the SCR. What I've noted on this thing here, on the SCR, what I've noted is that the output of the zero crossing, what they called zero here, is high when the AC waveform is high, and low and zero when the AC waveform is below zero. And this is why I wanted to check here how it is. So here it is just with pulses, which makes it a tiny bit more complicated, because we, instead of just checking whatever we want, we have to have an edge detector. I don't know. With microcontroller, it's super simple. Whenever I do bare boards, bare metal C, I can just have an interrupt service routine which tells me whenever we have the zero crossing. This way I have a very perfect timing. With this microcontroller here and with Arduino, I have no idea how this works. Because can I do that? The pulses, how long are the pulses? The pulses, yes, 1 millisecond, almost 1 millisecond long. You can see, yeah, a bit less than 1 millisecond, but it's still plenty enough. So what we will simply do is, because this will do almost nothing except sense the data, get some data. Can we do that? I don't know how to do the crossing. I'll do firmware is something else. We'll do firmware. I'll do firmware separately, and I'll probably read how we can do edge detection. And if not, I mean, the pulse is almost 1 millisecond long. That's plenty enough to verify it. The microcontroller here will only decode some from time to time, so UDP data, and send it over and parse it. There's not a lot to do here. So I think within 1 millisecond we have enough time to verify if the signal is high. And if the signal is high, then we've been to one of the pulses. And then we just count the we just count how much we want. Ideally, we want to have a timer which synchronizes to these pulses, and every time we have a rising edge or falling edge, we don't really care, but rising edge would be better. Then we use this as a new period, and within this period we set the PVM. That would be the ideal solution. I don't know if this is possible or easy to make with the Arduino. You can still write yourself in the register, but I have no idea what the registers for this ESP is, and I don't want to learn it. Maybe there's some code which is finished. Well, we'll see. Firmware is for me. Do it off screen, because firmware on screen is probably a bit boring. At least I find it boring when I watch other people code. But at least we know how this works. Now we want to switch on the lamp. So let's switch on the lamp. This is switched on. What we do is let's measure what is on this pin. Okay, so this pin, which is the how is it called? PSM, should be PVM. This pin is the input of the optocoupler, and meaning if we put it high, then the optocoupler is on, then we send a pulse to the triac. We'll simply try it with having it high. Yes, and whenever it is high, the power is on, and if we unplug it, the power is off. We just now I just want to make a tiny blimp, and it should be on just for half of a second or something like this. Let's try. Yes. So it is not. It is a tiny bit longer than the small connection I make. This means that the pulse doesn't have to be long for the triac to open. Actually, BTA 16. How long does the pulse need to be on the BTA 16? BTA 16. I don't think I have the datasheet for the BTA 16 on my computer. BTA 16. But we can find the datasheet online. BTA 16 from ST or something else, they're all the same. So triac. Let me add it. Let me put it to a screen. No, I'll just try to show it. I2C critical gates. Is there something with milliseconds? Absolute maximum ratings. Okay, this is not what I want. Milliampere gates. I've never read a triac data sheet. I don't do a lot of things with. Let me put it on the screen so you can also see it. You don't need your oscilloscope anymore because. Do you? No, you don't. Let me remove the oscilloscope. F9. So this is the data sheet of the BTA 16, and I want to figure out how long does the gate, probably, is it also called the gate? Yes. How long does the gate need to be high for it to enable before it can switch off? IG standard 20 milliamp. Okay, 20 milliamp, 20 to 50 milliamps. Oh, that's a lot. I hope that the microcontroller is able to provide 20 milliamp. Else I will have to add a transistor, but I don't want to add a transistor. I want to drive it directly using the pin. So non-repetitive surge peak on state current, full cycle 20 milliseconds. Yes, this is when we're at 50 Hertz, it is 20 milliseconds. Yeah, it's written even here, 50 Hertz, 20 milliseconds. Device critical raise on state current. Amps per microsecond. This is probably what we want. So if we want device critical rates of rise on state current, is this what we want? Critical rate of rise on state. Oh no, this is how fast it goes on once it has been enabled. We want to check how long we need to enable the PVM pin. Because what we want to do is we want to be able to, for the next zero crossing, to start low. If we are too late switching off the gate, we want the power, which we want. This is why I want to check the value. This over time, or 300 volt for per microsecond. This is 4 quadrants. Typical characteristic. This means we need at least 2 microseconds because. Oh, that's not the BTA 16. I don't know if I have AUC. Microseconds. Then 20 milliseconds because that's the. So this is far. Oh, on states. Thermal impedance versus pulse duration. But the pulse, I want my pulse duration. Pulse duration in seconds. 5. So that's 500 seconds. Okay. That's not what I want. Surge peak, number of cycles. Number of cycles, we don't care. On characteristics, relative variation, gate trigger current. So just we need a bit of current, then it goes on. I have no idea how Triac works. Well, internally, or how to read the data sheet. Thermal resistance, package information. Let's try for pulse. Pulse duration, that's the only thing that's there. That's also the only thing. Okay, I have no idea. I will just try it out, and if it works, it's good enough. I will think something like 500 microseconds. That's half a millisecond. That should be plenty sufficient to switch on a thing. I have to take into account that I want to be able to also be switch it off. So if I have a pulse of 500 microseconds, it means that I have at least 500 microseconds on at the trailing edge. So it could be even shorter. I'll just try whatever it works, and if I'm happy with the thing. I don't know if it's in the data sheet. Well, it's probably in the data sheet. I just don't know where to find it. Yep. So this works actually. We are done. Well, almost. Now I just need to wait the firmware and to test if we've tested that with 3 volts it works. We can see what the zero crossing is. The output, yes, if we switch on, the output works. 35 watts. Does it heat up? Let me touch it. Oh, I didn't expect it, but the heatsink, well, you can still touch it. It's not very warm. But it does heat a tiny bit up, although we just have 30 amps going through it. 30 watts, sorry. 30 watts going through it. But yeah, it's, I would say 5-10 degrees above ambient. Nothing to worry about. We don't need to put a fan. Didn't leave it for long, but it's plenty fine. Could check with, do I have it here? Yeah. Okay, this thermometer does not work. I'll try with the IR gun. What does the IR gun say? 30 degrees. Okay, plenty efficient. And we have it on for something like 1 minute, and it's not rising. At least I don't see it rising. So we don't need to cool it. Let's see on the board. Okay, 30. Okay, on the board it's a bit higher, 35. Oh, it does increase. Let's see how far it increases. Without moving, with the things. Well, also now we have the 30 watts always on. I don't know how much current the motor is taking. And we will not have it always on. We will have it off for most of the time because we don't really need a really fast speed. Yeah, 36, and it seems to be okay, 37. I think we don't have to worry about anything here. We don't need any active cooling. Passive cooling will be fine, even in the box. Some message. Fuck. Not important. Yeah, 36. Still touchable. Everything which is under 50 degrees Celsius is completely fine with me. And the lamp works. So the next step will be to write firmware to actually test it. We have the setup correctly on the breadboard. It kind of works. We didn't test it with the output pin, but we don't have any firmware. So I have a firmware, and tomorrow we will start testing the firmware. I'll try to write it this evening or tomorrow morning. We'll test the firmware, and tomorrow afternoon we'll meet again to put everything in the box, to put all the connectors where they want, where they should be. So everything in here, to put some connectors. We also want to monitor the tachometer, but that won't be too hard to monitor. And then we can test it, because tomorrow evening I will be in this club where I can try to install it, try to test if it works. I'm sure it will not be perfect from beginning on, but it's not critical. Looks like a mess on this bench, but that's always the case after a long project. But now I can switch off the light, remove the power, up, switch off the isolation transformer. Where's this damn? Yep, button. Isolation transformer switch off, and we are done for today. It was a short continuing, but at least we have the state. And so let's see tomorrow. Well, enjoy the short video, and we'll see you soon.